It's not possible to measure, or virtually impossible to measure longitudinal field inside the lightning channel. However, the variation of the vertical electric field as you move away from the channel is not very strong. In fact, if you are exactly at the boundary, the vertical electric field must be the same. So the tangential component of electric field is continuous across the boundary. So measurements at 10 centimeters can be used as proxy for electric field inside the channel. This is what we did. So we estimated input power and input energy for lightning channels. This is one example for one triggered lightning stroke. There are 4 traces here. At the top, electric field. There is a little portion, return stroke portion, measured using focal sensor, 10 centimeters from the termination point. The second trace is corresponding current, 12 kiloamps, kind of typical. The product of the two on the return stroke portion was used for field. This is power, and the peak value is something like 5 times 10 to the 8th watt per meter during channel length. And the integration of this signature over time gives energy, which is at 55 microseconds, somewhere between 2 and 3 kilojoules per meter, which is in agreement with some of the other estimates, but not in support of some other estimates. Moving further to the right on this, along this frequency scale, visible light. So this is the optical portion of the spectrum, visible light from 400 roughly to 700 nanometers, and the corresponding frequencies are somewhere between 10 to the 13th and 10 to the 15th hertz. Optical radiation is used for studying lightning phenomenology and mechanisms of various lightning processes. And I'm going to illustrate this for leader step formation mechanism and for the attachment process. So what you see here are 9 frames of a high-speed video camera showing the tip of the descending dust step leader. And the size of each frame, actually this is a portion of the frame, 20 by 20 meters, and it is 4.17 microseconds per frame. And the altitude of the leader tip is progressively lower with increasing the frame number. So it's not at the same altitude, it is actually the highest altitude, this is immediately prior to the return step. And what you can see here is actually indicated by white arrows are relatively bright segments of the channel that are formed below the leader tip. In this case, there are 2. One is less bright, this is more bright, quite bright, 2 of them right here. And these are similar to what is called spatial stamp in long spark experiments. And if this is the case, then the mechanism of step formation process that was inferred from long spark experiments is probably applicable to lightning. This is the first evidence from that shown on this slide. The mechanism that was inferred from long spark experiments is illustrated here, taken from Boring Hall in 1978. And on the left, there is a static picture illustrating the structure of the streamer zone right here. This one is the time resolved image, and the corresponding current record is shown here. It's easier to start with this one, the static picture. So we see the thermally ionized channel, primary leader channel here. So this is the leader tip, and for negative leader, as I mentioned earlier, there is space stem. There are actually 3 of them shown here, and then there are streamers. Negative streamers extending downward and positive streamers extending upward to the leader tip. And at some point, this space stem will start extending, and at that time it is usually called the space leader. And eventually it will join the previously formed channel, and the channel extends. This constitutes leader stem. Time resolved picture, more informative but more difficult to this region is a thermally ionized channel, the same type of shading as in the static picture. And these straight lines, they indicate streamers. Either positive is going up or negative is going down. And this is the point where the space-time starts extending. This positively sloped line indicates it extends upward, and negatively sloped line indicates it extends downward. And this is the instant when connection is made between previously formed channel and newly formed stem. At that time, there is a burst of streamers, very intense, from the newly formed leader tip, and this is probably the source of X-rays in light. And this becomes bright, current pulse is formed in that instant, and luminosity pulse usually propagates in the vector direction. This is a further information on leader formation process. This picture is taken from paper by Wong et al., published in 1999. This is for dust jet leader and rocket trigger light. And what is shown are the light versus time waveforms at different heights above ground. 40 meters, 40 meters, and up to 290 meters. And the time scale is 60 microseconds across. And the initial light signal appears at later times at low altitudes, which indicates overall downward progression of the leader. And this red arrow indicates this overall progression. At the same time, there are multiple pulses corresponding to individual leader steps, and with some effort, it's possible to track some of those pulses at different altitudes. For example, for pulse number 10, this broken line shows it's here, 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 and the positive slope of this broken line indicates that the progression is upward. So, this is consistent with what was inferred from laboratory experiments. The overall progression of the leader is downward, however, individual leader pulses propagate in upward direction, starting from the leader tip. The attachment process. This is the first optical image of upward connecting leader and rocket trigger light taken from another paper by Wong et al. This is a schematic representation of experimental data. Time scale is indicated here. This is the height scale. Upward leader is shown here. It lasts 400 nanoseconds or so, and made connection with the descending leader at a height of about 10 meters. And then there was a return stroke that initially propagated bidirectionally. Now, more recent data for upward connecting leader, which is part of the attachment process, are shown here. Two pairs of images. One is here, the other is here. It is the same image, but this is the original one, and this is the inverted brightness levels, negative of this one. So here we can see this is 56 meters height, and here we see the streamer zone just entering the field of view. It's probably 7 meters or so long, and in the next image, this is 2 frames before the return stroke. And this pair of images, again, this is negative of this one, is 1 frame before the return stroke. The next frame would be return stroke saturating the entire image. In this case, is extended 25 meters, and in the negative you can see the streamers from the kinks of the channel and also from the tip. And also there is a kind of a brighter segment here, which is similar to space stem, but in this case actually there is a faint filament already connecting the descending leader with the upward connecting leader, 16 meters long at this instant of time. So this is probably the beginning of the so-called breakthrough phase that will eventually facilitate connection of these bright leader channels. These are, for comparison, some images for long sparks. The length of the gap was 4.5 meters, and the polarity of high voltage electrode was negative in all cases. And these are 4 different images for 4 different sparks, not the same one shown in different instances of time. The exposure was 2 microseconds for the first 3, 0.5 microseconds